We're now ready to start evaluating some cosmological models. We'll consider several special cases. The first one would be a spatially flat, matter-dominated model, which is also known as Einstein-de Sitter model. We will then look at its version when it's dominated by radiation and not matter. We'll then consider what looks like, at first, superficial model. It's called Milne model, and it contains neither matter nor energy. But it is very instructive in some ways. And then finally, we'll look at the behavior of more general models. So let's first consider a spatially flat model with exactly critical density. This is also known as Einstein-de Sitter model because that's the one that two of them developed together in 1930s. And it's been used quite a bit, even though the universe we live in does not really correspond to it. But it is very useful as a description of an early universe. We'll start with the Friedmann equation, which we can then rewrite in the following form. From that, we can see the value of the time derivative of the scale factor a dot, or as expressed as explicitly as time derivative, it is plus or minus square root of the quantity shown there. This is very easy to integrate, as shown here, and the solution is shown here. We can just rewrite that and see that in the matter-dominated phase, universe expands as a 2/3 power of the time. Now let's look at a similar model, but this time dominated by the radiation. Recall that the radiation energy density changes with a steeper power of scale factor, 4 rather than 3. You get 3 for the expansion of the space and dilution of the number density of photons. You get an extra power for the energy loss due to the stretching of the wavelengths. All right, so here is its Friedmann equation, which again we can rewrite in the following form. And from that, we see that time derivative of scale factor is inversely proportional to the scale factor itself. That too is an easy one to integrate. And the solution is that the universe expands according to a square root of the time. Let's now consider what's called Milne cosmology. This is a spatially flat model, good old Euclidean geometry. It follows the special relativity, and it's idealized in the sense that there is no matter in it at all. It's an empty universe, just space. So you can think of it as galaxies having no mass of their own, just being test particles to show us how the coordinates are expanding. As you will see, Hubble's law follows immediately and directly from it. Special relativity still holds. Lorentz contractions are at play. And again, there is no special location. Cosmological principle applies. In fact, Milne was the first one to introduce cosmological principle. So this is a spatially open, negative curvature model with zero density. Its Friedmann equation is shown here, and since curvature constant is less than 0, we can see it here. Therefore, the time derivative of scale factor is constant. If it's constant, that implies a linear expansion. The universe expands as the first power of time. Or it can be contracting, since the square root can be of either sign. All right, now let's consider a slightly different version of that. Again, curvature constant is negative, but this time density is finite and positive. The Friedmann equation is now shown here. And this time, the square of the time derivative of scale factor is positive. Well, as the universe expands, time goes to infinity, the scale factor will go to infinity, and 1 over a scale factor will go to 0. And since the obvious inequality applies here, we see that in a asymptotic case, either matter or radiation-dominated universe will in the end behave just like the Milne model. Now let's consider a more general case, models in which matter, radiation, cosmological constant, or dark energy can be present. First, let us look at the model with a positive curvature. Here we can write the Friedmann equation again and transform it as shown here. Now, if the density declines as a 3rd power of the scale factor, as it would be appropriate for the matter field universe, or as 4th power, as it is appropriate for radiation, then in any case, the product of the density and the square of the scale factor declines as scale factor on power it's either -1 or -2. Since on the right-hand side we have a term that looks like that, minus a constant, sooner or later that whole side, the right side of the equation has to be 0. When the time derivative of scale factor is 0, that means that it's either at the maximum or at the minimum. However, look at the expression for the acceleration. The right-hand side must be always negative because both density and pressure are positive quantities. And therefore, the second derivative must be negative, which means that the scale factor has reached maximum. Then it can only collapse back. So in a model like this, recollapse back to the initial singularity or reverse of the Big Bang is inevitable. Now let's consider a model which only has dark energy in the form of a cosmological constant. Its Friedmann equation is shown here, which we can rewrite in a fairly straightforward fashion. And so now if we assume that scale factor is allowed to increase as long as needed, eventually the first term on the right-hand side dominates the second term, regardless of the actual value of the curvature constant k. So if the energy density of the physical vacuum or cosmological constant is positive, then the first time derivative of scale factor will be positive, and that means that that universe will expand forever. Now, if the energy density of dark energy is negative, and that's actually possible, things will get to be a little more complicated, but we need not concern ourselves with that at the moment. Now let's look at models in which both radiation and matter are present. And if their energy density is much higher than the energy density of the dark energy, which is certainly true in the early universe, then this is a perfectly good description of the early universe. The rigorous solution for the density as a function of time will be a little more difficult, but we can do the following fairly good approximation. We can divide the history in the time where radiation is dominant and when the matter is dominant. In either case, early on, the model is very close to flat, and so we can assume curvature of 0 to begin with. Since the density of the radiation always decreases faster than that one of matter, sooner or later those two curves have to cross. And so at earlier times, radiation dominates, and at latter times, matter dominates. And then each one drives the expansion according to the different power of time. So in general, we can rewrite Friedmann equation in terms that describe behavior of three densities as follows. This is actually a useful form, which we will use later on to derive expression for distances in cosmology. So let's recap again. Which component of the universe dominates its dynamics at what time? Since the fastest declining one is more important at the earlier times, and that would be radiation, early on, the universe must be dominated by radiation. Sooner or later, energy of the radiation drops below that one of matter, and then becomes matter-dominated. Eventually, the density of both matter and energy drop sufficiently to reach the level of the constant energy filling the universe, the cosmological constant, and after that, cosmological constant must dominate. So generally, it's always true that radiation dominates the early universe no matter what, and the present and the future universe will be dominated by the cosmological constant, or dark energy that behaves in that way. So we can express dynamics of the universe in very general fashion here, showing how scale factor depends on time at certain power, which is a function of the equation of state parameter W. During the matter-dominated phase, W is 0. Remember, when we introduced the equation of state, we said that for regular matter, there is no pressure, they're just test particles as far as cosmology is concerned, and the universe expands according to time to the 2/3 power. Since that power is less than 1, the universe is decelerating. It's slowing down its expansion. This was intuitively obvious because the gravity of the matter pulls everything back. Just as if you were to throw an object up in the air, it will reach certain maximum height while decelerating all the way there, and then of course it will turn and fall down. In the case of radiation-dominated universe, the expansion will be according to the time to the 1/2 power. And the universe will be decelerating. Again, since matter and energy are equivalent, energy in the form of radiation exerts gravitational pull, so it slows down the expansion. If the universe has a constant energy density, like a cosmological constant, W equals to -1, then when that term is dominant, it will drive expansion according to the exponential law. The dividing line between accelerating and decelerating models is at the value of the equation of state parameter W of -1/3. Since -1 is less than -1/3, this is the cosmological constant model, acceleration will dominate. And so here is just a plot that shows what some expansion laws look like. There are for different values of cosmological parameters that are written in the caption, and we will actually address those in more detail later.